All right. So without any further ado, let's get going. So I'd just like to start with a small overview of today's presentation. First, I'd like to give an introduction as to what Flownex SE is. I understand some of you might not be familiar with the software, so I'd just like to introduce it and make sure that everybody else understands. The next, I would like to discuss some of the needs for co-simulation in the world of computer-aided engineering. Then describe some of the options available for co-simulation in Flownex and demonstrate these features as well. And then finally, I'll conclude by highlighting some of these applications for co-simulation in practical industrial applications. Okay, so first off, Flownex itself fits into a category that we like to call flow network modeling, or FNM. This is different to traditional CFD in the sense that here we look at modeling systems with or very large systems or subsystems. The size is not so important, but the point is the flows inside of these systems are predominantly one-dimensional. The systems include both heat transfer and your conventional flows with pressure drop calculations. And the software itself, or this particular flavor of software, is designed to provide a very intuitive and very easy to use user interface where users can insert components to model the parts of the plant as they see it. So models would exist for pipes, for pumps, for compressors, for valves, for tanks, for containers, turbines. All of these components are represented inside of the components library, and then users can just choose components that are relevant to their particular plant, insert them, creating a small network very similar to a process flow diagram, and then the network itself can be solved and produce results for both the flow and for the temperature and heat transfer inside of the system. This type of modeling is based on semi-empirical models for the components themselves. So the models themselves are not done in the traditional sense of CFD with, say, a turbulence model. Instead, we have the characteristics of the flow inside of the components modeled using empirical correlations. So, for example, the frictional losses in a pipe are accounted for using Dasche-Fishbach or Hazen-Williams instead of a K-epsilon model. All right, so here are just some differences between the flow network modeling approach that we use in Flownex and the traditional CFD approach used by Ansys, or rather the traditional CFD and FEA approach if you start looking at some of their structural tools as well. In the flow network modeling environment, as I mentioned, we look at modeling plants or subsystems inside plants. So relatively large geometries or large sets of components. These models are done in both steady-state environments as well as dynamic or transient environments. The flow characteristics of the components are captured through empirical correlations, and the input data for these systems comes from process flow diagrams or component data sheets such as pump charts or turbine maps, as well as other network parameters. When we contrast that to the CFD and FEA world, we see that the FEA and CFD world tends to focus on detailed local component modeling. So the geometry involved is typically smaller due to the increased computational expense with the much finer meshes. The software itself also runs in both steady and dynamic simulations. Pressure losses and other physics are characterized through complex physics models, such as turbulence models. And the input data for these systems is typically via CAD models. So you can see that the two software packages have different approaches. One of them is more looking at a system level, and one of them is looking at more of a component level. So just a bit more background about Flownex itself before we start looking at some of the applications. Flownex itself is part of this flow network modeling category. It solves the conservation equations for mass, momentum, and energy using the semi-empirical models to provide correlations for inputs into these equations. We're able to construct networks of one-dimensional flows and two-dimensional heat transfer. The second dimension in heat transfer relates to P transfer in a pipe, for example, in the radial direction as well as the axial direction. So the framework is built in place to capture both of those dimensions for heat transfer. The solver inside Flownex is based on an implicit pressure correction algorithm. It's incredibly stable and results in very fast solution times. So in our networks, we typically see steady-state solutions in the order of seconds, and in the worst case of incredibly large networks, in the case of minutes. Flownex itself is included with the software are a bunch of analysis tools. We have a designer, optimizer, and steady sensitivity analysis functionality as well. We've included this because at the end of the day, the temperature or pressure inside of your network is not the result that the engineer is interested in. It's the pipe size, or the optimal valve opening, or the optimal flow rates, or understanding how sensitive your system is to a particular input that really matters. So all of these analysis features have been added into the software to allow users to interrogate their solutions as well. Flownex itself includes a large fluids library. This includes liquids and gas models, as well as two-phase fluid models. We can account for mixtures of gases and liquid gas mixtures as well. These are typically used in combustion examples, and we can also model settling and non-settling slurries, so typical non-Newtonian fluids. And then lastly, the software itself is developed within a NQA1 and ISO 9001 environment. So we have very strict quality assurance guidelines, or rather enforcement, and the software itself goes through a very rigorous verification and validation procedure in line with nuclear standards. This means that the software itself can be used for safety critical calculations in the nuclear industry. Okay, so this flow network modeling approach has very strong applications in modeling one-dimensional processes. So if we look at the image over here, imagine this is part of a power generation cycle. We might have a pipeline with a couple of turbines connected, and then heat transfer through a condenser. When we're looking at modeling these sections here, the components have been particularly well characterized. We have empirical correlations to provide information regarding the pressure drops and the heat transfer in these components. And these are very easily modeled inside of Flownex, or very easily modeled in the flow network modeling environments in general. However, when we look at more three-dimensional geometries, in this case I've just used a furnace for example. Here we have very complex three-dimensional flow patterns with intricate geometries, and this is not very suitable for the one-dimensional environments because we can't predict the flow paths, so modeling it with one-dimensional elements becomes impossible. So the need for 3D CFD immediately takes over here. However, the two the two components can complement each other incredibly well in some simulations. It's often that you might be looking at a system response rather than just a particular component's results. However, when it comes to your three-dimensional CFD results or your FEA results, you often make the decision based on the complex geometry or the high level of detail of results that are required. So in this environment, we're looking at using flow network modeling tools for one-dimensional flows with very well characterized components, and CFD for geometries that have not been characterized, or geometries that require very detailed results for analysis afterwards. So when it comes to co-simulating, when we start using the 1D and 3D packages together, we can actually start building high-level, we can start building large models composed of one-dimensional elements for 1D flows, and then supplement and then add in the three-dimensional models inside of this system as well. So we can have the best of both worlds, with the fast and easy to build networks in the one-dimensional environment, and the accuracy and detailed results from the three-dimensional models. The data transfer between these two is this actual co-simulation application that I'd like to talk more about today. The benefits of this is that we're able to get the very detailed results from our 3D CFD and characterize the flow through there incredibly well using our Fluent models or perhaps other CFD codes. And at the same time, we still get the reduction in our computational time by using codes such as Flownex. So our mesh can be, or our geometry that we're modeling, can only focus on the area where we need our high level of detail. So in the boiler, for example, we can start modeling our boiler at the outlets of our burners, as opposed to modeling them directly upstream and including some one-dimensional flows into the system. So it reduces the overall size of our mesh and can help in reducing our computational time for solving these large three-dimensional models. What's also useful in this this application is three-dimensional models often have boundary conditions specified in relatively arbitrary positions that are difficult to measure. So, for example, if you're trying to characterize the performance of your boiler and understand the heating inside of that and the temperature distribution, specifying boundaries at your boiler mouth, for example, might be a difficult place to receive measurements from your plant. So what is ideal is to use a 1D code to provide a means of calculating your conditions at the boundaries to your 3D CFD simulation, knowing measurements upstream of those points. So those upstream measurements are then analyzed using the 1D code, and the downstream results at the boundary for the 3D CFD can be calculated. So it forms a nice way to provide the boundary conditions for your 3D simulations with seamless data transfer. So we minimize the chance of any user error when it comes to transferring data between two software packages because they integrate seamlessly between each other. Okay, so today I would like to talk about just a practical example of this. An example that we're using is the modeling of the HVAC system for a server room. So in this environment here, we have 6 server racks and air flowing through this room to cool these server racks. The air supply system, through the actual heat exchanger to cool the air, the fan itself, and all of the ducting required to pass the air into the room and remove the air from the room, is all one-dimensional in nature. So it becomes a very good application for Flownex, whereas the flows inside of the room itself are three-dimensional in nature and have incredibly complex flow patterns, so are then best modeled in something like Fluent. So the way in which we do this is to use our Fluent coupling, our Ansys Fluent coupling. The first step in this procedure is to generate a case file. So once your Fluent simulation is built, you can, through the menu, you can click File, write a case file for Fluent. This is basically a file that documents all of the settings for your simulation as well as the geometry for your simulation. We then link this file to our simulation inside of Flownex through our Flownex coupling, our Fluent coupling, apologies. This then allows Flownex to reference that case file, and as soon as we run Fluent in its server mode, we can actually pass this information to Fluent, execute that model, and transfer data between Fluent and Flownex. So the first step would then be to generate this case file, insert that into your Flownex project files, and then run Fluent in server mode. This here is just a batch command. It's a very simple line of scripts. Ultimately, it's using the AAS command to run Fluent in server mode. So once we do this, our Fluent interface opens. Okay, and then if we go back to Flownex, what's going to happen is we're going to transfer information from our network to our Fluent coupling. The Fluent coupling is then going to transfer that information to Fluent itself, solve the simulation, and then transfer information back to this network. The network itself on the left-hand side here represents the inlet to the server room. So the fan itself, a heat exchanger with refrigerant flowing on one side to cool the air, the ducting into the room with a restrictor to account for the pressure drop through the vents. Then the boundary condition, which will be our interface between our 3D and our 1D CFD. We then have another boundary condition at the other interface, followed by a restrictor again, some ducting, and then an outlet to atmosphere. So when it comes time to solve the simulation, our data is exchanged through parameters. This is a very common practice inside of many of the Ansys tools. You can create input and output parameters inside of Fluent. Those input and output parameter names are then specified inside Flownex, and we're then able to transfer results or transfer inputs to the Fluent file by means of our data transfer links here inside Flownex. So if I run the simulation right now, it's going to take the information from our flow rates here in this system and the outlet pressure of this system and the inlet temperature, transfer that to Fluent, and then begin iterating the solution. So this information is being passed through input parameters. You'll see, apologies, the simulation is running at the moment, so I can't open this. But this information is passed into Fluent, and then the Fluent simulation begins to iterate. Once the simulation is complete, it then sends parameters back to Flownex. The parameters I've chosen for the simulation is the pressure at the inlet here. So this represents the back pressure for this portion of the 1D network. It also then sends back the outlet temperature and the mass flow rates at the outlet. So all of this information is then exchanged between the two simulation codes, and our results are basically, our two simulations are solved in parallel. Okay. When it comes to analyzing the results of this, we can now just save our results from our Fluent in server mode. So over here, we're simply able to write data files, or we could even, if we save this entire project, we could then open it in Workbench and perhaps analyze the results through the link into something like CFD post. Alternatively, we can just input that data file and then analyze the results afterwards. So this here shows the temperature distribution on the server racks itself. It's just a scalar plot where the color represents the temperature. And then this over here shows the flow pattern inside of the server room. So the coloring here represents the velocity of the flows. So using these two, using the co-simulation environments, we're able to put together our entire system in a hybrid 1D, 3D model. We're then able to solve these two models simultaneously with data transfer taken care of in the background. The units are completely accounted for, and the user basically just needs to specify the correct links from Flownex to the parameters inside of Fluent. All right. The next thing is that the applications for co-simulation don't stop in the world of CFD. They can continue into structural analysis as well. So we have a mechanical coupling as well. This allows users to connect Flownex simulations to Ansys mechanical simulations as well. And a particular example of this is analyzing the stresses inside of a boiler during a startup scenario. So this here just represents a typical wall inside of a boiler with the holes for these are just obstructions in the tubing. So this geometry here, all of the pipes would then be modeled inside of Flownex, and the heat transfer would be accounted for inside Flownex as well, and we would solve for the temperature distribution inside all of these tubes. That information would then be transferred, this information being transient because we're looking at a startup of the boiler. This information would then be transferred to Ansys Mechanical, and a stress simulation can be done for the entire boiler as a whole. We're then able to highlight areas of high stress and either look at redesigning the geometry in these areas to avoid stress concentration, or perhaps even altering our startup protocols. So perhaps ramping the boiler up a little bit slower or a little bit faster, and seeing what effect that has on the thermal stresses inside of the system as a whole. Okay, so those two couplings that I showed you here, the Fluent coupling and the mechanical coupling, have been our couplings inside of Flownex for a while now. Our developers have been busy with a latest coupling. This is not released yet, but it will be released in our production build that will be available in the next few months. This coupling itself is directly inside of Workbench. So it provides users the very familiar environments of Workbench that they're used to, and allows you to integrate your Flownex simulations directly into that. So what I have here is just a little example. We have a traditional Workbench environment over here with our CAD geometry connected to a mesh, that mesh transferred into Fluent, and then solved, and then post-processing done in CFD post. We can then install a Flownex add-in, which is incredibly easy to do, and then we're able to drag in a Flownex component just like we would any other Ansys component. This can then be linked to a Flownex network, so we add a link to a particular network file, and then from this information, Flownex can then configure the inputs and outputs of this simulation and transfer them into Fluent. The way in which we do that is through parameters. Inside of Flownex, we have parametric study functionality. So what I have here is just a parameter table. We're able to drag in values from our simulation. Let's say we would like the pressure or the temperature at a particular element. So I'm just going to take this node, for example, and take the total temperature. If we want to add this to the parameter table, all we have to do is just drag and drop that into one of the columns of our parameter table. This then provides the interface for inputs and outputs of Flownex. When we then import this network into Workbench, it appears in all of those parameters are then read and then appear as lines here in the configuration setup for our Flownex component. We then simply need to select whether or not they are inputs or outputs. A few of you might recognize this. It's very similar to the Excel interface, and basically allows you to then specify whether or not these parameters in Flownex should be treated as inputs or outputs for the Flownex components inside of Workbench. Once these are specified, they will appear inside of our parameter set. We can then configure dependencies inside of here, and then Workbench will handle the data transfer between the different components. So in this case over here, I would like to take the outlet pressure from Flownex and transfer that to the inlet pressure in Fluent. So to do that, we have the outlet pressure here as our parameter 9, and then for the value of our bend inlet pressure, this is the value that will be applied to the inlet boundary condition. We simply, in the expression box, type in the name of the parameter that we would like. This then establishes the link between the two and sets up the dependencies, and then Workbench handles the data transfer from there. Okay. This also allows you to then simulate not only between Flownex and Fluent and Ansys Mechanical, it also opens up many other tools inside of the Ansys suite. So we're then able to use any of the tools that ship with Ansys and now connect our Flownex simulations to that as well. So this allows us to work with CFX simulations or even LS-DYNA simulations and connect these to our Flownex networks as well. Okay, so just to round it up, I'd like to talk about a few additional applications for this. So we already mentioned that we can look at HVAC from a building point of view. This can also be extended into the automotive sector, where we start looking at modeling the HVAC systems for traditional automotive or automobiles, basically. So here we would model the refrigeration or the cooling system, as well as the vents for the car inside of Flownex, and then have the airflow and the radiant heat sources inside of the cabin be solved using something like Fluent, for example. This can also be extended into the aerospace industry as well as the defense industry, where you could be calculating or designing the HVAC system for perhaps a small passenger aircraft, or even a vehicle in like an armored vehicle in the defense industry, where you need to ensure that the HVAC system is correctly configured in that environment as well. This can also be put into other industries. Turbine modeling is another particularly good application. Flownex itself has a large library of secondary flow components. This is used in modeling compressors and turbines. And we can then use that to simulate portions of our gas turbine or our compressor that we're analyzing, where we would like boundaries to be established for a detailed 3D CFD simulation. So perhaps you're modeling a portion of your combustor and would like to have Flownex calculate the conditions inside of the compressor. We can then have all of that modeled, and then the boundary conditions can be transferred into our 3D simulation for our combustor. Alternatively, we can look at even more localized models where Flownex can be used to calculate boundary conditions for these environments, or perhaps even move to a system level model where we insert the full geometry of our compressor turbine arrangement, and then have Flownex calculate the system level conditions around that. So model the other parts of the plant, be it the dampers for controlling airflow or other parameters. We can then make adjustments to those to simulate different load cases, and then Flownex will calculate the relevant input boundary conditions for our CFD simulations. This thing also extends into many other applications in the processing industries, where once again you're looking to simulate the conditions inside of a container or some kind of vessel, or perhaps some kind of processing environment. But once again, the boundary conditions at that container interface is not available due to the difficulty of measuring at that point. Here we can then build a simple Flownex model which can transfer the information from a known point in our plant through the components between that point and our vessel that we're looking to model, and then seamlessly transfer that information to something like Fluent for use in the 3D simulation investigation. All right, so just to conclude, Flownex itself provides an ideal one-dimensional tool to complement your three-dimensional simulations. So using all of the features that I mentioned, and can be used in many different applications in your 3D CFD environments. The ease of use of it is really appealing, as well as the seamless data transfer. So it removes the possibility of human error in terms of transferring information from one simulation package to another, and it also takes care of a lot of the nitty-gritty work in between there. So it's incredibly easy to configure and provides a very robust solution. Like I mentioned, we have the direct couplings for Ansys Fluent and Ansys Mechanical inside of Flownex, and then in our latest release in a few months' time, we should also have the Workbench integration as well, which could be used with for co-simulation with any of your other Ansys products. All right, that sums up about everything I have for today. If you would like, we can discuss some questions right now. I'll get to them in a second. Alternatively, if you would like to try the software, or if you would like a demonstration with some applications particular to the industry that you work in, you can contact us either through the email address sales@flownex.com, which is at the bottom right of the slide over here, or alternatively through our website. There is a section for requesting a demo, and we'll get in touch with you, organize a meeting, and present some of the applications of the software to your particular industry.